Hi, welcome back to the second part of my talk. And in this part, we will dive more into more details on about the proofs of our main theorem. We'll talk about the Chekhov-Ilya-Ashburn DGA and functor of augmentations and Kalman. And we also establish the correspondence between fieldings and clusters. So let's begin by doing a quick review of the CEDGA. The Chekhov-Ilya-Ashburn DGA is an algebraic invariant of the Legendre links. As an algebra, right? So it's DGA. So we start with an algebra. It's an algebra is generated by generated over Z2 by ripcords and formal variables associated with mark points. Right? So we're actually going to decorate our Legendre, our positive braid closures with mark points, right? And the grading is given by a master of potential, and the differential can be computed by certain inverse discounting, right? So this is a very quick review of the CEDGA. If you want the full definition, please check out our paper. It has like a full section on the definition. But actually, we are not studying the DGA itself. We're actually studying the augmentations of the DGA. Right? So an augmentation of the CEDGA is a DGA homomorphism from the CEDGA to a trivial DGA, right? And we actually use an algebraically closed field of characteristic 2, put it at degree 0, and 0 anywhere else, right? So an augmentation is a DGA homomorphism epsilon of this form. The augmentation variety is basically the moduli space of augmentations of the CEDGA. When the CEDGA is concentrated at non-negative degrees, which is true for all the positive braid closures, we can see that the augmentation variety is actually the spectrum of the zeroth homology of the CEDGA. Right? So the zero homology is itself an algebra, and then you take the spectrum, right? So you get the augmentation variety. In our paper, we decorate the positive braid closure by placing a mark point at each right cusp. Right? So the resulting augmentation variety can actually identify it with a non-vanishing locus of a single polynomial function on an affine space, and therefore the augmentation variety is smooth and affine. Right? So let's talk about how you actually parameterize augmentation variety. Right? So there is actually a degree 0 ripcord associated to every crossing of the positive braid. So in this case, you have 9 crossings. So I have 9 ripcords here, and for each crossing, you can also associate a matrix. So this matrix represents some sort of partial discounting, right? So imagine that you have positive braid closure, so you also have strands above, so you can start counting partial disks, right? And this matrix records how many partial disks you have on the left of this, or right past this crossing. Okay. So for example, for the first crossing here, we have Z3 of B1, so it's the third crossing, crossing on a third level, so it's Z3, and the labeling is B1, so it's Z3 B1, and the matrix is of this form, right? So you can do this kind of matrix, you can construct these matrices for each crossing along the positive braid, and then you can multiply them from left to right. So you have Z3 B1, Z1 B2, Z2 B3, Z1 B4, Z3 B5, and so on. Okay, and then we call the resulting matrix M. So in general, right, you can do this for any positive braid beta, positive braid word beta, and let's denote the determinant of the K by K submatrix at the upper left-hand corner by delta K. Then the augmentation variety is actually the non-vanishing locus of the product of these determinants of submatrices, right? The product from 1 to n of delta K M, right? So this is a polynomial function on the the affine space AL, right? L is the length of the braid, and we want it to be non-vanishing. Okay, so that also shows that the augmentation variety is of dimension L. Right. So one theorem that we proved is that the augmentation variety is actually a cluster K2 variety. Okay. So next, let's so we're going to talk about this this more later, right? So it's not enough to just say something is a cluster variety, right? So it's not interesting enough, right? What we show later, it's actually there's a correspondence between clusters and fillings, right? So to do that, let's talk about fillings. So as we said in the part one of our talk, right? So we actually focus on the specific types of fillings. We do not just take fillings in general. So we call an exact Lagrangian cobordism an admissible cobordism if it is a composition of the following four kinds of building blocks. Right? So you can have a saddle cobordism which pinches a degree 0 ripcord into two parallel lines. Right? So saddle cobordism. Second type is a cyclic rotation, which takes, so since we're talking about partial braid closures, you can always take the last crossing and then move it to the front via the upper arc, right? So this can be achieved by Reidemeister 2 moves. Right? You can also go backward and rotate things from left to right. And then you have the braid move, which is Reidemeister 3. And then lastly, you can fill up an unknot. So if you see a maximal TB unknot anywhere, you can fill it up with using the unique exact Lagrangian filling of the max TB unknot. So Honda Kalman constructed a contravariant functor that maps Lagrangian links to the CEDJs and map exact Lagrangian fillings, exact Lagrangian cobordisms to DJ homomorphisms. Right? So this is a contravariant functor, right? For cobordism from lambda minus to lambda plus, the DJ homomorphism goes from lambda plus to lambda minus. Right. So this functor exists in general for all cobordisms, but for the admissible cobordism, they are computable. Right? You can actually compute them explicitly and see what action does. Right. We can dualize this contravariant functor by taking the spectrum of the zeroth cohomology and obtain a functorial algebraic variety morphism going from the augmentation of lambda minus to the augmentation of lambda plus. Right? So in this case, the functor becomes covariant again, right? So start with cobordism, making it an algebra homomorphism, contravariant, and then go back to a morphism of varieties, which is covariant again. Okay. So a theorem that we proved is that for any admissible filling of a positive braid closure, the functorial morphism is an open embedding of an algebraic torus, and its image is a cluster chart. And if you have two fillings that are Hamiltonian isotopic, two admissible fillings that are Hamiltonian isotopic, then they will correspond to the same cluster. So one quick remark, there's actually more geometric meaning to this cluster chart. So what you can actually interpret the cluster torus chart as the moduli space of trivializations of F star local systems on the filling L. In particular, right, Ti being the mark points, right? So they are the mark points on the link, and they record the monodromies around the link component, right? So since the links are boundaries of the filling, right? If you take the product of all the monodromies, that should be 1 because that's homologically trivial. Right? So this is one remark. Second remark, we have actually written a program which computes for any admissible filling, we can compute its EHK morphism together with its cluster. Right? So I'm going to switch to the browser and show you this calculator and how it works. You can find the calculator on my website. Let me share a different browser. Okay, so this is the calculator. So let me just take some example. So say you have a 4-strand braid, and the braid word is this. Okay, so you can draw the positive braid. So this is drawn here, and on the right you can find information about this positive braid closure. For example, it's finite point counts. So this finite point count is actually related to the Humphrey polynomial in some way. And then you can do all sorts of moves to this positive braid. For example, I can do a braid move, which I can do it here, right? And then I can pinch some crossings. For example, this one and this one, right? I can exchange these two crossings, right? So this does nothing on the link, but the computer somehow sometimes when you need to do like braid moves, you need to commute the crossings to the right place. Right? If there's a crossing on some other level, although not related to the braid move itself, right? But if it's in between the region, the program will get stuck. Right? So sometimes you need that kind of moves. So let me pinch one more crossing, like this one, right? For example, if I want to do a braid move here, I have to commute these two crossings. Commute these two, move this crossing out of the way, and then you can do another braid move here. Right? And then you can do a counterclockwise cyclic rotation, and then another one. And then let's pinch the rest. Okay. So after you finish pinching all the crossings, now you see now you're done with the filling, because you just fill up each so each level is going to be a knot, and then you just fill it up with the unique exact Lagrangian filling for the max TB knot. And here's the quiver associated to this filling. On the right, so this records the mutation sequence from the initial seed of the cluster variety. And then this records the moves that you have done so far. And this gives you the EHK morphism, right? So how are the ripcords mapped under the EHK functor. And then lastly, right, these are the cluster variables. And then the final part is a reality check to make sure that the image is a torus, so that so the PIs are local coordinates on the torus, and then the cluster variables, as you see here, they're all monomials in terms of the PIs. That tells you that the cluster variables are also coordinates on the torus. Okay, so yeah, feel free to play with it, and if you see any bugs, please report to me. Yeah, let me switch back to the slides. Okay, all right. Okay, so here it's an example of the cluster structure on the truffle, the 2-3 torus link, torus knot. So as we said earlier, this is the matrix M that's obtained by multiplying the partial discounting matrices, and then the augmentation variety will be the non-vanishing locus of this polynomial. Okay, and as a result, you actually get 5. So topologically, any filling will look like this, right? And you will get 5 cluster charts based on the sequence of pinchings. So there are 3 crossings, so you can pinch them in 6 different ways, 6 different sequences. Turns out that 2 of them give you the same filling and also the same cluster, which is this one. But then all the others are different. So you get 5 cluster charts, and these 5 cluster charts the famous pentagon associated to the type A2 cluster variety. Right? So if you talk to a cluster person, this is the A2 type cluster variety is probably the first cluster variety they will tell you about. Right. So now let's talk about how we actually prove our main theorem. So this is the cyclic rotation. So we proved it using the cyclic rotation and related to the cluster DT transformation. Okay. So we define the full cyclic rotation to be the exact Lagrangian cobordism, which cyclically rotates the crossings of beta one by one from right to left. So you have a positive braid, so you rotate each crossing from right to left counterclockwise, one at a time. Right after you finish all of them, right, you get back to the same braid wood, the same front projection. Okay. So the theorem that we proved is that the functorial isomorphism between automorphism on the augmentation variety corresponding to this full cyclic rotation is equal to the squared of the Donaldson-Thomas transformation. So the Donaldson-Thomas transformation is a special kind of automorphism on a cluster variety, which is related to the Donaldson-Thomas invariance of certain 3 RBL categories. Right, and some special property of the DT transformation is that it permutes the cluster charts on the cluster variety, and another result about it is that it is acyclic. Oh, sorry. If the quiver of the cluster variety is acyclic and infinite type, then this DT is known to be of infinite order. Right. So therefore, a quick corollary is that suppose the augmentation variety has a quiver that's acyclic and of infinite type, then any admissible fillings of then you can take any admissible filling of this positive braid, and then you can just post-compose it with this cyclic rotation many times, and for different k you get different exact Lagrangian fillings, because they are all different charts, because DT is acyclic. It's of infinite order. Sorry, it's aperiodic, I should say. It's of infinite order. Right, so here's a picture of it. So you start with the link, you can fill it up with any admissible filling that you like, and then you can just keep composing this automorphism, and it's guaranteed that every time you compose, you get a new filling based on the cluster theory. Right, so this deals with positive braid closures that have acyclic infinite type quivers. Like, what if they don't? If they don't, we employed an exhaustive argument and show that as long as your positive braid is not, your positive braid closure is not Lagrangian isotopic to those exceptional cases, then there's always a positive braid gamma with an acyclic quiver of infinite type, and also admissible filling connecting this new link with the link that you are looking at. Right? So, so suppose you have this admissible cobordism K, then you can make use of lambda gamma and precompose it with all different kinds of distinct non-Hamiltonian isotopic fillings, right, like this. Right? So you, as a result, you get infinitely many distinct fillings as well. Okay, so I guess this is the end of my talk. Thank you for listening, and I would like to thank the organizers for inviting me to speak at this workshop as well. Thank you.